everyone, Rhoda here with a JAC capsule about trigonometry. I'm wondering if I presented you with this empty Cartesian plane and asked you to sketch the graph of y equals tan of x, would you know how to fill it in? If not, let's go through it together. Now, one option would be to look it up and then memorize it, but I'm going to try and explain it in a way that makes more sense, and it's going to be some good practice working with the unit circle. So first of all, we need to know that tan of x is equal to sine of x divided by cosine of x. I'm going to use that and my knowledge of the unit circle to come up with the graph. The first thing I notice is that this is a fraction, and the fraction will not be defined if it creates a division by 0. So anytime cosine gives me a value of 0, that would mean that tan of x is undefined because I can't divide by 0. So let's figure out where is cosine equal to 0. You could do that using the graph of cosine if you know that really well, but I'm going to use the unit circle. I know on the unit circle that cosine is the x value, so x equals 0 anytime I'm at the y-axis. That's these two positions here. Now, which angles are at those positions? We have a whole video about the unit circle, so I'm going to jump right to the answer. I know that this is pi over 2. If I count in the positive direction, the first thing I hit is pi over 2. If I count a little farther in the positive direction, all the way around to here, I get to positive 3 pi over 2. Or I could also reach these points by going in the negative direction. So counting into the negatives, I reach this point at negative pi over 2. And if I keep going into the negatives, I reach the top point again at negative 3 pi over 2. So those are 4 places where cosine equals 0, and that means that tan would involve a division by 0. So tan doesn't exist there. I'm going to mark those on my graph. That's at negative 3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2. So I don't quite know yet what's happening at those points, but I know that I can't draw any graph there. All right, next thing I'll do is the same thing, but for sine. I'm going to look at my fraction. Tan is sine over cosine. If sine is equal to 0, then I'll have 0 divided by something. That's equal to 0. So let me figure out when is sine equal to 0. Anytime that happens, tan would also be equal to 0. Going back to my unit circle, I know that sine is the y value. So where the y value is going to give me 0, that would be on the x-axis, here and here. Now I need to know which angles those are. Well, the first one would be 0. Then if I go a half turn around, I reach positive pi. If I keep going a full turn around the circle, I reach 2 pi. Going into the negatives, I could go a half pi around in the negative direction, that's negative pi. Full turn around in the negative direction, that's negative 2 pi. So the places where tan would be equal to 0, out of what I can see on the graph right here, are at x equals 0, x equals pi, and x equals negative pi. The next thing I'm going to do is quite a bit trickier, but it's a really great skill to have for calculus class. It's going to come in very handy, especially if you're in the science program. The next thing I'm going to do is just pick a region of my graph and think about what are sine and cosine doing on the unit circle in that region. I'm going to start by looking at the area where x is between 0 and pi on 2. On my unit circle, x equals 0, or my angle of 0, would be starting here. And I want to think about going from x equals 0 until pi on 2. So I'm thinking about as my angle travels through this first quadrant. The first thing I'll notice is that in that first quadrant, the x and the y values on my unit circle are both positive. In other words, sine and cosine are both positive. So in this area here, tan is going to be positive. What else can I notice? Starting at 0, we have sine is 0, cosine is 1. So that's why I got a value of 0 there for tan. What happens as I move up? Well, if I think about values near 0, I'll see that sine is smaller than cosine. So when I divide sine by cosine, I'm going to get an answer less than 1. So something close to 0. But as I move along here, as my angle increases, the difference between sine and cosine is getting smaller and smaller and smaller. And that means that my values are going to increase until eventually sine and cosine are equal. And that's going to give me a value of 1. Now what happens as I continue towards pi over 2? I know that at pi over 2, tan is undefined because cosine is equal to 0. What if I'm just a little bit before pi over 2? On my graph, that would mean that my x value is something a little bit less than pi over 2. On my unit circle, that would mean that my angle is very close to pi over 2, but not quite there. In that case, my x value would be a very small positive number. In other words, my cosine value would be a very small positive number, and my sine value would be something close to 1. So it would be around 1 divided by a very, very, very small number. When you think about a very small number, think about maybe 0.01, just as an example, just to make you realize that when I divide by something very, very small, I'm going to get a large answer. So that means that as I'm approaching pi over 2 on the left-hand side here, my y values are getting bigger and bigger and bigger. That's creating a vertical asymptote. And we saw that when we're close to 0, we're getting small positive numbers. So this quadrant plots out like this on my graph. I wonder if you could think about what happens as your angle travels from 0 until negative pi over 2. That would tell me the graph over on the left-hand side of 0 here for tan. Try to think about that. Pause and unpause when you're ready for me to do it. Let's go through it. So if I start at the angle 0, and then I go to the left on my x-axis for tan, or in other words, my angle goes into the negatives on my unit circle, what's going to happen? Well, if I think about a value that's very close to 0 but less than, I can see that my y value would be negative because I'm under the x-axis. My x value would still be positive, and that means that I'm going to get a negative value for tan. So tan would be negative down here. The other thing I'll notice is that when I'm very close to 0 on the left-hand side, my y value is going to be a lot smaller than my x value. So that means that sine is going to be a lot smaller than cosine. So when I divide them, I'm dividing a smaller number by a bigger number. That's going to give me something small. If that's not clear to you, you can think of an example. If I divide 0.1 by 100, that's going to give me a smaller value. So that tells me that I'm having negative numbers that are quite small when I go to the left of 0 here. So I could try to draw that, something like this. Now, what happens at the other extreme in this quadrant? As I approach negative pi on 2, if I think about something just before I reach negative pi on 2, well, my sine value is still negative, my cosine value is still positive, so tan is going to be negative still. And I can notice here that my y value is now much bigger than my x value. So my sine value here is a lot bigger than my cosine value. So the situation has flipped. I'm dividing a bigger number by a smaller number, or you could think of it in the way that we did in the previous case. I'm getting something close to 1 divided by a small number. That's going to give me something very large. It's large, but it's in the negatives. So as I approach negative pi over 2 on this side, I'm going to have very large negative numbers. So again, I get an asymptote, this time going down into the very large negatives, or going towards negative infinity is another thing that you could say there. This is a really good strategy to use. If I keep doing it, I'm going to understand the unit circle more and more. I'm also going to understand what happens when I approach an undefined value, which is a really important topic in calculus. So this exercise that we're doing here is actually a little bit of pre-calculus prep. That's why I would really encourage you to try and do another segment. Pause the video and think about what would happen going from positive pi on 2 until pi on my unit circle. That would be over here in the second quadrant. Try to think about that. See if you can draw the corresponding graph for tan. When you unpause, I will do it too. So if you did it, you should have got something like this, and I'll take you through why. If we think about angles a little bit bigger than pi over 2, on my unit circle, I'd be somewhere over here. Now, that would mean that sine is positive, my y values are positive, cosine is negative. So tan here would be negative. Next, notice that when I'm very close to pi on 2, my x values are way smaller than my y values. My x values are very close to 0. My y values are very close to 1. So 1 divided by something tiny, that gives me something large. So I'm getting large negative numbers when I'm close to pi over 2 on that side. That's why I drew the line that I did here. Now think about what happens when you get close to pi. I know that at pi, my tan value will give me 0 because sine is 0. What if I'm only close to pi though? I'm not quite there yet. Well, tan would still be negative, and this time my y values would be much smaller than my x values. My y values would be approaching 0. My x values would be close to 1. That's going to give me a very, very small number, but remember that it's a negative number. So that's why I drew this part here, very small negative numbers going towards 0. You can probably see where this is going. And if you try the next section, we could try going from pi to 3 pi over 2 over here. You're going to get something like this. So this is actually just a recopying of the piece that we had before between negative pi on 2 and pi on 2. Tan actually recopies itself like this between every pair of vertical asymptotes. So every place where cosine is undefined creates a vertical asymptote, and between each pair, we get this same exact shape. Mine don't look all the same because I'm not a great artist, but they should be identical. So tan actually has a period of 1 pi. It recopies itself over every pair of vertical asymptotes, which are always 1 pi apart. That's a great thing to know about tan. Of course, instead of asking you this about tan, I could have asked you this about cotan. Well, be aware that it's much more important to know the graph of tan, but you should be able to figure out the graph of cotan either by using the method that I just showed you for tan, only this time cotan is cos over sine. Or if you remember the graph of tan, you could use the fact that cotan, in addition to being cosine over sine, is equal to 1 over tan. So what you could do is look at your graph for tan and think about what would happen if I took the reciprocal everywhere. How would that change the behavior? You can stop and think about that for a sec, and then I'll just quickly present you with the answer. So here's my graph of tan once again, and if I scroll down, here's my graph of cotan. What you can notice is that the places that used to be vertical asymptotes are now places where I cross the x-axis. That's because with tan, I got vertical asymptotes when cosine was equal to 0, but with cotan, if cosine is equal to 0, then cotan would be equal to 0 as well. Also, the places where I hit the x-axis for tan, those were spots where sine was equal to 0, but for cotan, if sine is equal to 0, that would create a division by 0, so that becomes the places where my vertical asymptotes happen. For the rest, you could think about taking reciprocals, because cotan is the reciprocal of tan. If I flip the value around, positive values stay positive, negative values stay negative, but a number that used to be really big, when I take the reciprocal, becomes really small, and vice versa. That explains what you see here. It's not as important to know the graph of cotan. What you should probably know is the graph of tan, that it looks like this, that it has a period of pi, and that it has these vertical asymptotes at every odd multiple of pi over 2. Hope that helps. See you in the next video.